Hi guys, Audrey here. So today we're going to talk about when to use the comparison test versus when to use the integral test. So the thing is, we've seen that the integral test, ideally we're going to avoid it as much as possible. We're going to prefer the comparison test, the limit comparison test, the ratio test, the root test, p-series, geometric series, test for divergence, anything else we're going to try first. So that said, sometimes when ln is involved, the comparison test can still be used. So let's just think about these two problems, ln n over n squared versus ln n over n to the fourth, and see if we can kind of logically come to a conclusion about when it's better to use the comparison test versus the integral test, or the integral test versus the comparison test. Okay, so let's start with this first problem here. So the test for divergence in both of these things, actually, the limit as n approaches infinity of ln n over n squared is going to 0, and over here the limit as n goes to infinity of ln n over n to the fourth is also going to 0. So in both of these cases, the test for divergence fails. And the reason for that is we know that ln n grows quite slowly. We've seen that ln n will grow more slowly than n to the fourth or n squared, or really into any power, any positive power at least. We could also do L'Hopital's rule a few times to see that this happens. Actually, I think we'd only have to do it one time for each of them. Okay, so that said, test for divergence fails. So let's go back and think about ln n over n squared. So this kind of looks p-series-ish. We have n to a power, and then we have that ln n on top, and that ln n is the thing that's stopping it from being a p-series. So what we're going to do is we're going to think, okay, well, we don't want to use the integral test if possible, so let's start off by bounding ln n. So I know that ln n is less than n. This is one of the things that we've learned. We showed it by doing a limit. We could have done L'Hopital's rule here and shown it again. Ln n is less than n. So when we're doing a comparison test, remember we use squeeze theorem ideas. We want to multiply or divide by whatever necessary to get back to the thing that I started with. So here I'm going to multiply by 1 over n squared, 1 over n squared. Now 1 over n squared, that's always positive, so my sign isn't changing. So ln n over n squared is less than n over n squared, which is equal to 1 over n. So if I were to compare this to something, it would make sense to compare it then to the harmonic series, which is the sum of 1 over n. And I'm just going to draw a little line down the middle here so that we can kind of keep them on each one on this proper side. So we know that the harmonic series diverges. So then the thing that we would want, the inequality we would want to be true, would be that ln n over n should be greater than 1 over n. But we already showed that that's not true. So that's not true. So then we might think, okay, well, let's go on to the limit comparison test. My inequality failed, so try limit comparison. But for the same reason that the test for divergence fails, the limit comparison test will also fail. Because if I'm doing limit as n goes to infinity, ln n over n, and then remember I flip the other thing, n over 1. So like that ln n is just going to give me an infinity right here. So I get infinity, which means the test for the limit comparison test fails. And most of the time when there's a ln n involved, the limit comparison test is either going to result in a 0 or infinity and therefore fail. Okay, so in this case, we tried comparison, it didn't work. It didn't work because the inequality we came up with did not end up being what we needed it to be, and the limit comparison test then failed. Okay, so that is our sign that now maybe we should go and try the integral test. So for the integral test, the thing that we want to be true is, or that we need to be true rather, is that this needs to be continuous. And well, it is. So the only place that it might not be continuous would be for some negative n value. because that would be plugging a negative into ln, or for when n squared equals to 0, so for division by 0. So the answer is that yes, this is continuous, only discontinuities not on interval. And the only discontinuities in question, those would be in less than or equal to 0. Okay, so then the second thing is this needs to be positive. And again, the answer here is yes. And it's positive because ln n is positive for n bigger than 1. Well, we're only looking at n bigger than 1. And n squared is also always positive. N squared always positive. Ln n greater than 0 for n greater than 1. Okay, so then the last one is maybe a little bit more challenging to think about. And that is it decreasing? So we know that ln n grows more slowly than n squared, which tells me that it's probably decreasing. Like, that gives us a pretty good intuition that the thing that we want to be happening is happening. That said, it's not really enough to count as a proof. So we're going to actually take the derivative of this thing and show that it's decreasing. So we're going to think of, is ln x over x squared decreasing? Well, ln x over x squared prime, we're going to apply our quotient rule. So this is 1 over x times x squared minus ln x times 2x, all divided by x squared squared. So this is x minus 2x ln x over x to the 4th, which is x times 1 minus 2 ln x over x to the 4th, which is 1 minus 2 ln x over x cubed. Okay, so now the question is this thing right here less than 0? Well, that x cubed doesn't matter because we're really only looking at positive x values. It's kind of like our n starts at 1, so our x also starts at 1. So that x cubed doesn't matter. So this is like saying 1 minus 2 ln x. Is that less than 0? Well, that's like saying, is 1 less than 2 ln x? And well, we know that ln x after e becomes bigger than 1. So like, yes, we can see that this is true. We can see that this is true at this point, but we could also finish. So this is like saying ln x, ln x greater than 1/2, which gives me x greater than e to the 1/2. So this is true as long as x is bigger than e to the 1/2. Which means that we can say that this is decreasing for x bigger, not x, we don't care about x anymore, we only care about our n, and we're going to do this in black actually. So this is decreasing ln n over n squared, decreasing for n greater than e to the 1/2. So like eventually it's decreasing, we're good. So what that means is we can apply the integral test. Now notice the fact that we are having to apply the integral test, it would have been great if that comparison test had worked. This is one of the reasons that the integral test is like last resort. We have a lot of things to show before we can even start doing it. And then once we start doing it, we still have an integral. So now we're looking at applying the integral test. And we end up with the integral from 1 to infinity ln x over x squared dx. I'm actually going to immediately write this one as a limit. Limit as t approaches infinity 1 to infinity ln x over x squared dx. We're going to do the indefinite integral. Which is going to involve an integration by parts. So we'll have the integral of ln x times x to the negative 2 dx. We can use Liate, our mnemonic device, to see that our u and our dv, our u should be ln x. So our du is 1 over x, and our dv will be x to the negative 2. We want the integral of that, so our b will be negative x to the negative 1. We stop there. That left side is not going to 0. It's not repeating itself. So we end up with this is equal to negative ln x over x plus the integral of 1 over x squared dx is equal to negative ln x over x plus negative x to the negative 1 plus c. Okay, now we're going to go back to our limit and get that this is equal to the limit as t approaches infinity of negative ln x over x minus 1 over x between 1 and t, which gives me the limit as t goes to infinity, negative ln t over t minus 1 over t, plus ln 1 is 0, plus 1. And now this 1 is just a constant. This right here is just going to 0. That 1 over infinity gives me 0. Ln t over t, that's going infinity over infinity. That's giving me that indeterminate form. So I'm only going to apply L'Hopital's rule on that part. So we're going to say this is like negative 0. I don't really have to write that, but I am. Plus 1 minus the limit as t approaches infinity. I'm applying L'Hopital's rule here. Derivative of ln t is like 1 over t over 1. So this is going to 1. Alternatively, I could have said, hey, I know t is growing more quickly than ln t. So then that thing, oh, I'm sorry. Yeah, so then that thing right there is going to 0. So what we had here is that this right here was going to 0. So we had that 1 left over. So we could have said, or ln t grows more slowly than t. So the integral converges, which means that the series converges. Okay, so that was a little bit long, and it was a little bit long because we had to apply the integral test, and the integral test involved taking the derivative to show that it was decreasing, actually evaluating the integral. Then we had a L'Hopital's rule that showed up in our limit, except we didn't actually have to use L'Hopital's rule. I just did to show you how long that this thing can get. Let's go back now and look at the other problem. And let's think about the comparison test that we tried to do over for this one. That comparison test will actually work here. So we have ln n is less than n, which means that if I multiply this by 1 over n to the 4th now, I get that ln n over n to the 4th is less than n over n to the 4th, which is equal to 1 over n cubed. So we want to compare to the sum 1 over n cubed, n equals 1 to infinity, 1 over n cubed, which is a p series. My p is equal to 3, which is bigger than 1. So this converges. So then what I want is for ln n over n to the 4th to be less than 1 over n cubed, and this was already shown. So this one right here converges by comparison. Okay, so notice that n to the fourth versus the n squared over there really wasn't much a difference between these two things. Why did the n to the fourth one work for the comparison when the n squared didn't? And that has a lot to do with ln n and the shape of this thing. So I want you to ask yourself the question now, without actually doing it. Do you think if you had ln n over n cubed, the comparison would succeed? What about if you had just ln n over n? Okay, so I want you to think about that and hopefully you'll get to the right answer. That's all. Bye, guys.